My name is Bharat Naik, and I'm a software engineer here. Lunch will be served after this session, so be kind. So the goal of this section of the presentation is to basically expound on the material presented by Rob. So specifically, we'll go into the storage proxy, what its responsibilities and capabilities are, and then do a deep dive of the backend, figure out what the basic building blocks of the backend are, and how they come together to form this scale-out distributed storage platform that we and our customers are so excited about, right? So the first part is going to be like a recap of what Rob mentioned. The proxy is a piece of Hedvig software bundled together as a lightweight VM running on the compute node. Its responsibility as a proxy is to redirect requests from the VMs on that compute node to the backend cluster, right? So as you add more compute nodes, each of them contain a proxy, and they're essentially independent of each other, right? And we'll come to how that helps, right? So
the number of proxies is unlimited, so it just depends on the on my infrastructure,
exactly,
my architecture.
Right. So it's mainly kind of load balancing. So if you feel like a proxy is getting overloaded by a lot of VMs, you add another compute node, migrate some of the VMs there, and so effectively it's load balancing. But we'll also see what other advantages it has, right? Like Rob mentioned, the primary abstraction that the backend provides is that of a virtual disk. So a system administrator will carve storage out of the backend cluster, which means he'll basically create a virtual disk. This will in turn be exposed to the proxy, which masquerades as an iSCSI target or NFS server, and then exposes that to the client VMs to be consumed as an iSCSI LUN or an NFS share, right? So the VMs talk to the proxy via iSCSI NFS, and the proxy talks to the server or the backend via a set of APIs that are exposed by the backend, right? Now these APIs are programmable APIs, so the system administrator, for example, can directly use those APIs to provision storage.
How are you protecting the proxies? Are you doing that through any type of fault tolerance or anything?
Right, so the proxy logically is one, but physically it's an HA pair. So if one goes down, it automatically moves on to the other. So some more details about the proxy. It's intelligent in the sense that it has some idea of where the data for the client VMs it's responsible for resides on the backend cluster so that it can redirect requests appropriately, right? It also tracks performance of the server nodes in terms of latency. So it knows which node is behaving how based on its statistical analysis that is done based on previous requests, right? So it can intelligently route requests to the closest node based on latency. And we'll again see how it does that.
So you said it was stateless. Or I think you said it was stateless
yes.
earlier on. But presumably you are actually keeping resources or using resources in there for performance purposes. So
exactly.
there must be RAM or some
cache
sort
or
of,
SSDs.
some sort of SSDs.
So there is caching on the SSDs, except when it goes down and comes back up, it's completely invalidated. So it becomes fresh again, right? So that's about the proxy. Any more questions?
You said it was stateless, but it also has an understanding of how the data is mapped on the back end?
In memory, it will hold it as and when it services requests. And then, I mean, it's all stateless in the sense that if it goes down and comes back up, that state is gone. So it has to relearn it as more requests come. So on to what a virtual disk is, right? So I'll move on to this section of the whiteboard. So as I said, the primary abstraction provided by the backend is that of a virtual disk. There are a slew of options that you can turn on or off on a vdisk granularity. We'll cover the complete list during the demo, but I'll just mention a few of them which I'll require for the later part of the presentation. Right? So for example, the first is replication factor, or RF. So this primarily determines how many copies of this virtual disk you want to maintain on the backend cluster, right? So we support anywhere between 1 to 6, with 3 being the default, right? So this can be turned on or off at a vdisk granularity. Another term that is related to replication factor is quorum. So we define it as more than half. So mathematically it will look something like this, right? And its significance will come during the writes. But I mean, the usual question that's asked is, okay, so suppose I choose a replication factor of 3. Does it mean that I'm going to write to all 3 nodes and then act back? And the answer is no. We write to a quorum synchronously, and the rest is asynchronous. And we'll see how, what it manifests in and how we kind of handle that, right? Second is replication policy. So we support 3 replication policies: agnostic, rack aware, and data center aware. So agnostic basically says spread the data for this virtual disk anywhere you feel fit, as long as you maintain RF number of copies. Rack aware says maintain RF number of copies, but ensure the data is on nodes on different racks. And data center aware says maintain RF number of copies, but ensure there are nodes on separate data centers, right? So as we'll see later, the system is very good at balancing the data across the cluster, but what this allows the user is to have some modicum of control over where the data resides, so that there's a good balance between spreading the data across the cluster while still adhering to certain restrictions that the user might want to place. Right? And third, we have dedupe, compression, and client caching. So again, all of these can be turned on or off at a VDIS granularity. Dedupe compression is self-explanatory what they are. Client caching basically means cache the data blocks for this virtual disk at the proxy, right? So it will cache data blocks only for virtual disks which have client caching enabled, and provided the proxy has SSDs. So any questions regarding the policies?
Is this read-write cache or just?
It's a read cache.
Read cache.
So writes always make it to the backend, but reads can be cached at the proxy. Essentially because the proxy is stateless. Right?
So,
Yeah.
so the storage disks are not connected to the proxy, right? It's not a server.
Yes, it's a completely different tier. They are connected only to the nodes on the backend.
And that needs to be on bare metal or can be also a VM.
The backend? Yeah, so if it's hyper-converged, they will be on a box, but as VMs, right? But in a hyperscale environment, they will be bare metal.
Okay.
So who provides the locking mechanism for your NFS data? Because you've got lots of proxies accessing
Good question.
shared LANs.
Right. So essentially what we have is a mechanism to ensure what we call timestamps, to ensure that conflicting writes are able to be separated and thought of differently. And we have a mechanism here itself which ensures that you generate monotonically increasing timestamps for conflicting requests. So that is handled at the backend layer.
So you lock at the back end rather than at the proxy.
I wouldn't call it locking in the sense that it ensures that you'll get different timestamps for writes at the same time, but we are dependent on the clustered file system to do the locking for us.
Okay, and how do you sort of cater for things like, because obviously I think the idea is you're expecting this to be very distributed.
Right.
So how do you cater for the situation where you might have a slow proxy or something that's on a slower network, and therefore, that becomes more difficult to keep up to date? I don't know, does that have an impact at all?
No, I think the question you're asking is more pertinent if in a VM environment, you're typically a single writer environment, right?
Or in a VM environment, yes.
Yes.
But I'm not thinking necessarily of being.
So if you think about it, if you were going to take that analogy further and look at bare metal, for instance, if you're a block device, unless you're having a clustered file system sit on top of that block device, it's still a single writer. You have a single file system, single writer, right? So, and even in our NFS use cases, we have put techniques in there where it will look like a single writer to us, right? And that's too much of detail to get into now.
Okay,
I will
fine.
definitely expand that for you
We don't have
guys.
to go into that level of detail.
Yeah.
I just,
So we are protected on that front.
Okay.
If you're using it if you want to use our NFS as quote unquote general purpose where you have multiple writers, then what he alluded to will not be the way things work. It works slightly differently.
right. Okay.
So if the proxy has to manage all the writes, but actually it doesn't cache and
Yes, so the
doesn't
proxy
give the-
redirects the writes to the backend cluster as appropriate.
Okay, so the latency becomes higher because you have to do 2 hops before.
So
getting to the-
he's going to talk about how the writes work in a second, and when he says that, you'll get the flow of how writes
Yeah.
work.
Is the deduplication span virtual disks? I mean,
Yes,
the
it is
main-
global deduplication. So deduplication can be turned on or off at a VDIS granularity, but for all VDIS that have dedupe enabled, it is global across them, right?
So on what block size what block size is the dedupe?
We support both 512 and 4K.
Okay.
512 block size and 4K.
The fact that you can remove deduplication and compression, it means that it has an impact, because it has an impact on performance, because some of primary storage vendors, they say it's always enabled because we of course don't have an impact or visible impact on the way we manage the duplication.
Right. So suppose the user starts with, say, dedupe and compression off, right, and then realizes that he's getting into a state where he wants it on, right? He can, and we'll show that during the demo too. He can just take a snapshot and clone and choose a completely different set of features for that. So he can change these settings after a snapshot and a clone, and then those features will be enabled for those features.
Yeah, but the duplication has an impact, right?
In our system, no.
Okay.
And again, so a couple of things. I think the question could be construed in a confusing manner to the guy receiving the question. So just to be clear, the reason why we keep these properties at a virtual disk granularity is because deduplication and compression, their effectiveness is ultimately determined by the kind of data that you put on the system.
Yes, of course.
Right? I can put cryptographic data. There's no way you can deduplicate that, right? Now, that's why we do it at a per virtual disk. So we assume that anyone consuming the storage asset knows what kind of data is going to go there, and you turn it on for those workloads. And given that he will expound more on how the global deduplication actually works and where you can actually take the distributed aspects of the system to actually drive down the effects of deduplication in traditional systems. Does that make sense?
No. No, I'm sorry. My problem is even if it does make sense because you are storing encrypted data, okay? If it doesn't not have any impact, why don't have it always on?
Where's the deduplication done? Is it a background process or inline?
It's inline.
It's inline. So at the time the proxy is sending data to the back-end storage system, wherever it is, before the data actually gets in the memory in the storage system, it's deduped.
Yes.
Yes.
So inline, if you have a very dedupe
Without any impact.
There is a little bit, there's no zero.
Now we're there, okay.
So you're going to hash the data. You're going to find out the hashes are someplace else before you write it, right?
So impact is 0 or epsilon. Now,
So let's come to the dedupe part, how it actually works, and then we can revisit this question.
Okay.
So let's move on to
I just wanted to clarify.
a few more terms.
I know.
A few more terms before we move on. Containers and storage pools.
nothing's free.
No, you're absolutely right.
So these are not Docker containers. These are Hedvig containers. So suppose you have a virtual disk, right? And you create a virtual disk of, say, size 1 TB. And all default parameters, so RF3 agnostic. But say you have a 10-node cluster, right? Now, you do not want all the data for this virtual disk to be located on only 3 nodes, just because the user has set an RF3, because there are other ways you can satisfy that. So what we do is we chunk a virtual disk into logical entities called containers, right? And each container is assigned a replica set. So, for example, container 1 might be assigned nodes 1, 2, 3. Container 2 might be assigned nodes 4, 5, 6, and so on. Like as the system sees fit, we'll assign replicas to the container, right? And say you add another node and there is no replica set assigned for, say, some container, say 11, and it will assign it to the new node that you added and some other nodes. So it's just to.
So for each virtual disk, you're actually assigning an address space to the cluster nodes to how it's going to.
Yes, so you chunk it up logically into containers so that you get that spread over the entire.
At a virtual disk level.
At a virtual disk level, yes.
How big are the containers?
So it's the number we have chosen is 16 gig, right? So I mean, if you make it too big, you don't get a good enough spread. You make it too small, the metadata overhead of maintaining stuff at a container level will kind of increase. So we chose 16 gig. Can it be 4 gig? Can it be 100? Yes.
Yeah. Okay.
So that's with containers, and storage pools are like I'm just introducing this because you'll see them later. Within a node, we group every 3 disks into entities called storage pools. So these are logical entities again, because within a node, a container gets assigned to a storage pool, right? So you might have these 3 disks and a container assigned to this storage pool. Now what it does is the data for this container is striped across these 3 disks. So as you write to a container, the writes actually happen across 3 disks, and that's what a storage pool is. And we'll see all this in the demo, but I'll be using these terms as I talk, so just to introduce them. Right. Any questions?
Do you do any rebalancing when you add new nodes?
Yes.
And can you evacuate nodes? Can you take a node?
Yes, so you can scale out and scale in, because essentially a scale-in operation is you lost one replica, right? So the system automatically decides what other replica should I choose, and it will just assign 4 and then rebalance the data and so on. And scale out is essentially, like I said, you add another node, the container gets assigned that node. So that's essentially scale out and scale in. Any other questions?
And if you decide to change the replication factor for a virtual disk, can that be changed after it's created?
You need to take a snapshot and a clone and just...
And use it to snapshot as a different...
Yes, so once a replication factor is assigned to a vdisk, you cannot change it unless you snapshot it, clone it. Doing the clone operation, you'll get the same list of policies, everything again, and you can set it at that time.
And you can...
A good example of why that you'll see us repeat that, snapshot clone. Like for example, if you had a production database, for instance, right, and it has a set of parameters that are very important to kind of a production environment. Now, if you want to give your application developers a development environment, but with the same data set, you can snapshot it, and when you clone it, you can completely change the properties of the original vdisk. And that's what the developers would get. Like for example, you could have a virtual disk that is perhaps DC aware in its replication policy, but for test dev, you probably don't need that. So you can change it to agnostic and keep it local to the data center. So you can do all these kind of tricks.
Okay. So I was just going to say, if you're distributing nodes geographically where they're not all in the same response time, and therefore you may have differences in performance levels as you're trying to write to those stripes, would you prioritize where you lay the data out, or where you put the container stripes based on latency of nodes and things like that?
As long as it adheres to the policies of the virtual disk. For example, if the customer said, I want this vdisk to be DC aware, I need to definitely keep them on different data centers, right? And the way we do it is we will choose nodes that are performing well at that point. And anytime if a node is spiking, we do this rebalancing process again, and as long as again adheres to this policy.
So the one thing that we do, which will become clear when you do shows you the guys the demo, is when you choose a DC aware, we also allow you to choose which data centers you want it replicated into.
Right.
So you have complete freedom in how you want to choose your replica set. Right? We have customers who are running our stuff, and there will be more talked about in a future conversation. But if the cluster spans like 4 data centers and they pick their replica sets such that 2 are close to each other and 1 is slightly farther away, and the system kind of is implemented in such a way that that long distance will not be reflected in the latency that the app will see. And we
will come to that, right? Yeah. And also what Avinash mentioned about the test dev stuff, that again is something that one of our customers are running, and we'll explain when Chris talks about real world deployments. All right. So coming back here, what we have in front of us is a 6-node cluster. This demarcation can be racks or data centers. So assume it is data centers. So this is 2 nodes per data center. Each node consists of 2 entities, what we call pages or the metadata process, and H block or the data process, right? And we'll come to what that is. So for example, H block or the data process is concerned with replication and locally storing the data. Right? So the proxy will redirect the write request to a H block process, and it will tell it where to replicate it. So the HBlock process doesn't have any say in where it should replicate, but it will tell you, the proxy will tell the HBlock process where it should replicate it, and the HBlock process will store it locally and do the replication. Right? That's its role in the cluster. So it's it has pretty marginal influence over the entire cluster, but within the node itself, it can choose which storage pool to place this container in. Right? So that's basically its role. All right, and this is just introducing the terms till we come to the Hedvig IO part. Right. Now the pages process, on the other hand, so the pages process is the more intelligent one. The pages process running on each node talks to each other and forms this distributed entity which is omniscient in nature. So it has entire global knowledge of the entire cluster. So not only does it know which nodes are up or down at any given point of time, it also knows the state of those nodes. So for example, if a node is getting spiked with like disk usage, right? If it's getting heavily loaded, it can decide to migrate data off that into someone else, right? It also knows for each block where it has been successfully replicated to, so that when a read comes, it can tell the proxy where exactly to go. Right? And like for example, if you add a node to the cluster, it can figure out that a node has been added and then rebalance the data as it sees appropriate. Right? So
the HBlock process runs across the client, the server, and the proxy, or is it running
so it
at
runs
the server?
on the nodes in the backend.
So it's running on the storage server.
On the
only.
storage server nodes.
And it understands how it's going to replicate, so the data would come to one server and then be replicated from that? Is that how it's done?
Exactly, yeah.
The proxy doesn't do it automatically for you?
The proxy will redirect a write request to a node and tell it where to replicate it, and the replication will be done by the HBlock process running on that node. Does that make sense?
Yeah, I'm trying to figure out how the container stuff gets factored into where the HBlock is written, and so,
So I can answer that right now, or
No, it's okay.
when the IO part comes in. Right?
Do it when you got it.
So given the fact that the pages process knows exactly where a block has been written to, right, it can answer interesting questions like, given a block of data and its hash value, has this block of data been written anywhere in the cluster? And this is exactly what allows us to do global deduplication. Right? So for example, you wrote a block of data on this node and say RF3, and so you wrote it across the data center, and a write request for the same comes somewhere here with the same hash value, right? The pages process can figure out that this data has been written already, this data with this hash value has already been written in the cluster, and so this block gets deduped, right? So that essentially is how global deduplication works, and I'll go into a little bit more into it, but this is what allows us to do global deduplication. The fact that the pages process is omniscient in nature. Any questions there? All right. So let's get into the.
So as far as the configuration of the system, it's either a 512 byte block or a 4K byte block, and then after that, it's always going to be that? Is that how it works? Or
At a per VDisk granularity, yes.
is it a VDisk level?
Yes.
Okay.
All right. So on to the Hedvig IO part. So let's look at writes first. So you have the proxy, and for the sake of this discussion, let's take a 3-node cluster. I'm going to draw the HBlock and pages process separately, but they're essentially one entity within a node. So this is the pages, this is the HBlock. Now, when a write request comes to the proxy, it's essentially a iSCSI CDB or NFS RPC. So given this offset, I want to write this data to it, right? That's essentially what it is. Looking at the offset, the proxy can figure out which container it lies in, right? Because the containers are homogeneously chunked. So once it knows which container it lies in, it first consults its own local stash and sees if any replica sets have been assigned to this container or not, right? If it's a fresh write to a container, the first step it does is it queries the pages process and asks it to assign replicas for this container, right? And the pages process uses its global knowledge and the fact that this VDisk has this policy, this replication factor, and assigns replica sets to the containers, right? So the first step is assign replicas to container. Now, any other writes to this container need not do step 1 because the replica set has already been assigned, right? So the proxy caches that information. The second step is write to HBlock. So now the proxy knows where this data needs to be replicated. So it sends the write request to one of them, right? So it sends the write request to say this node and tells it where it needs to be replicated, right? So what this node does is it forwards the request to the nodes that it needs to be replicated to and writes it locally, and then waits for a quorum to respond. And the quorum is what I had already introduced earlier, right? So in this case, the quorum is 2 since the RF is 3. So the moment this guy responds, the ACK is sent to the proxy, right? So if this is a high latency tier, this will be done asynchronously, right? So once step 2 is done, the third step is inform the pages process that this write has been successfully replicated, and this update is done atomically across the pages, and then it's a successful write.
So the second replica talks to the first replica and not actually directly to the proxy.
So the HBlock process that received the request is a person who talks to the proxy, and everyone else talks to the guy who sent him the request, which is this HBlock process, right? Now the obvious question is, what if this write to the third guy failed, right? So how do you ensure that you still maintain RF? So there's a background process that detects this, that runs on the pages process, because it will know if a write has been failed, because this asynchronous response, if it doesn't come, the proxy will tell pages that this write was not successful here, and this gets updated, and so the background process will repair these blocks in the background, right? So you will ensure that a quorum has always been met since the write was successful.
So it chooses a different location at the end.
No, it will repair the data on this host by taking data from any of these two, because the write is successful on these two, right?
So to acknowledge the write, it has to be done between 2, and it could potentially wait for whatever the RF setting is.
It doesn't wait. So it waits only for a quorum to be met. The moment the quorum is met, the write is sent, the ACK is sent back to the proxy. Whatever happens in the background, if it fails, pages process will know about it and it will repair it in the background.
What happens if I
What if
lose
it fails completely?
Then then this write is retried from the client because it's an unsuccessful write.
Okay.
Every write will time out at some point if the
Yeah, I mean if you break the tier between, right? So
you'll have to retry the write.
Okay.
right. Any other questions about the write?
And to answer your question about the wait, there is it's kind of a logical wait. I mean, the ACK back happens when a quorum returns, but it does logically wait for the third one in the background.
In the background.
And if you don't get it, then it informs the pages process that I didn't get this write that was destined to that node. And then the background processes kick in to repair those failed blocks.
The proxy is doing that.
No, the guy who received the write, yes.
The proxy will know when this guy informs it that the third write didn't succeed, and it will inform the pages. So that's the flow. But the pages is the one who initiates the background repair.
So allocating container space in a storage pool on a node happens at block write time, or?
No, so yes, in a sense that when the first container has been written to, the container gets assigned to a storage pool. So thereafter, all writes to that containers will go to the same storage pool, unless storage pool is getting loaded, and then he will plan to move it to another storage pool or a completely different node.
And the container size is 16 gigabytes. Is that what you said?
Yes.
Yes.
So if you take a virtual disk, every contiguous 16-byte chunk,
Is written
a
in one-
16 gigabyte chunk is a container.
Yeah.
So if you take a 1 terabyte vdisk, you will have 64 containers. And that's why the amount of state that we need to keep to know where the containers are replicated are very, very small.
Yeah. Right. And that's why the proxy, just by looking at the offset, can figure out which container it is. Sorry, I'm not going to rub this.
So are you thinking about parallelizing that process also?
Which process?
The rights to the
Quorum members.
yeah.
You mean
So
2
it's,
and
it's
3?
serialized, right? You write to the first one, and then he writes to the rest of the quorum.
No, it's not. It's
He writes to
actually,
all of them, but then he comes back with the quorum.
the writes locally take place in parallel. You don't want to parallelize them from the proxy because the proxy runs as a VM and it's hence slightly impotent when compared to the horsepower that we can have on the storage nodes.
It's almost like you're transferring the data between the proxy and the first H block process, and then it transfers it to the replicants.
The proxy receives the write from the hypervisor,
Yeah.
right? And then just pushes it out to one of the H blocks, which takes care of the entire replication.
So that's one
pipeline.
transfer, right,
Right.
to the H block, and then the H block transfers it to each of the replicas.
To maintain the RF, yes.
The question is, do you want to try to do that transfer in parallel rather than serialized?
Yeah. That's it.
I mean, in parallel, you can't parallelize it beyond what we parallelize
Well,
it
if the
today.
proxy, well, yeah, I mean, there's different ways of doing this. Obviously, the proxy knows which H blocks to write to, it could do it, but it's now responsible for replication rather than the H block.
No, and the problem with pushing it from the proxy is the proxy runs in a virtualized environment, so it's already kind of impotent. And if you're sending the same packets over the network multiple times, you've basically degraded your network utilization at the proxy by a factor of the replication factor per vdisk.
Yeah, so we want most of the heavy lifting to be done by the server nodes.
Is that done? Is it, so between those nodes, is that a dedicated network or is that just shared for whatever's already?
Standard IP network.
Yeah, standard IP network.
Okay, but it's not like dedicated NICs or anything like that. It's just okay. Is it 10 gig, 40 gig?
10.
10.
gig
Today,
Okay.
yes.
All right. So now that the writes, we know what the writes encompass. So the reads is well, simple in the sense that, again, the proxy gets basically given this offset, tell me the data for this, right? Now, the first thing it does is, sorry, I just need to draw this. The first thing it does is query the pages process and ask it where this data was successfully replicated to, right? So it will give you a list of hosts because depending on the RF, right? And then it chooses one of them since it's mirroring, so it can go to any one of them. It chooses one of them to get the data back, right?
Randomly or?
Yeah, so that's where it comes to tracking the historical performance of the server nodes. So it has the statistical analysis of the latency and chooses one based on that, right? So it will redirect the read request to say a read request to any one of them and get the data back, right? Now this is where I can introduce the caches. So for example, when a write was successful and the data was persistent in pages saying this block was successfully replicated to say these nodes, the proxy then caches that information in a cache called metacache. So this we recommend be on SSDs. So because you get more space, but if not, it's persisted in memory, right? So what happens is step 1 doesn't need to be performed during the reads, right? Because it can satisfy, it knows where it was successfully replicated to just by looking at the metacache, right? Now the second thing it can do is after a successful write, it can cache the data blocks too on the proxy side, right? And this is where we introduce the next cache, which is block cache. Now, obviously, this is done only for virtual disks who have the client cache enabled, right? And if the proxy has SSDs. So what this eventually allows you to do is not even do step 2, right? So read requests can be entirely satisfied by the proxy itself.
So metacache can be on RAM
Or SSD.
block cache only
Yes,
on SSD.
metacache is metadata, so it's really small, but block cache needs to be on SSD.
Can you select it? Or even if I have SSDs, I can choose metacache on
Metacache is always enabled, right? So we need some RAM because it's a very, it's something that needs to be done during the reads. You don't really want to go to pages. Data cache, since it's tunable at a vdisk granularity, if you don't really care, you can turn it off, right? But if it's on, you need SSDs on the proxy to cache the data blocks, right?
Did you say metacache was both in DRAM and SSD?
No, it can be in either DRAM or SSD. If you don't have SSDs, keep it in DRAM. If you have SSDs, we prefer you have SSDs so that the metacache can be there. Now the block cache is deduped, right? So there's a lot of space savings on it. And secondly, since you look at this, as you add more compute nodes, each of them which contain a proxy, the read performance is essentially scales linearly with the compute nodes because there's no dependency between the compute nodes, right? As reads go to a proxy, it can just satisfy that read locally and send it back. So read performance scales linearly with the compute.
Is there something like write around? That, like
Yes, it is write around.
Okay.
Right. So after write is successful, you write it back into the cache. Right. Sorry, it's write around for readers that are not cache enabled. It's write through for readers that are cache enabled.
Yeah, okay.
Right.
Can I add one thing
Yeah.
here? So if you look at this diagram here, we have a proxy per compute, right? The proxy here is only responsible for serving I/O requests for VMs that are running on this particular compute. So as you scale your compute, each one gets its own proxy. So the cost of caching is constant, right? You have really distributed your metadata caches at the proxy, right? And you can do the same even for block caches when you have SSDs or PCIe devices over here.
You can have multiple proxies per host, right, if you want?
We actually, like he had mentioned upfront, it's logically one, but there are two as an active passive pair, so if one goes down, the other takes over.
Right. So
And how are those sized? Are those sized based on your deployment?
yes, so the block cache is give it as much as you want because the more you give, the better. Meta cache, the same holds true, but it's usually sized around, I think, around 32 gigs per proxy. Usually it should be more than enough because metadata overhead is very, very small for us. Right. So does that answer your question? Yeah. Okay.
We have seen customers who have had NVMe at the proxy for block cache, and they were able to drive like 90,000 IOPS for reads. And that just scale linearly as
Yeah,
they
so
added
if
the
you add like 11, 12 of them, it's like 1 million IOPS from the compute node itself.
From cache.
for reads. Yes.
From cache.
If your working set fits in there.
Yes. And
Depends on the working set size. Yeah.
so this is how the read and write works, and the only aberration to this is dedupe. Right? So when a write comes in for a dedupe enabled virtual disk, the first thing the proxy does, even before step one, is figure out whether I should even be writing this data to the block, right? So it contacts pages which has this knowledge, so it can figure out, it can tell it whether to write or not. If it has to write it, it goes through the exact same process and updates the metadata process for this particular block ID, right? But if not, it can just update pages directly, no need of the replication, and just act back.
So the hashing is done at the proxy?
Yes.
The hashing is done at the proxy, yes. It's the hash is sent to the pages,
Right.
right?
So why didn't you choose to do write caching in the proxy? And acknowledge it to another one, just to...
Stateless.
Stateless, and you need to and you need to maintain the RF, so you need to give those guarantees for each reader, so you want it to be persisted on the backend.
This is the one thing that we have taken that we have not so far, despite being tempted quite a bit to, is to sacrifice correctness in the system in any way or form, right? At any cost. There are many vendors who actually, absorb the writes in SSDs and act back and then try to lay it out.
Because remember, the redundancy
It's not 100% foolproof in my mind.
The redundancy comes from the edge block process, so there is no redundancy at the proxy. So if you write it and act back and say the SSD crashes, or the whole proxy itself crashes, right? So you have lost your data. So that we don't allow. So now this is where the third cache comes in, which is dedupe cache. So again, only for readers with dedupe enabled. Instead of, once it knows that a block with this hash has been written to pages, it actually persists it in dedupe cache, so that next time you get a write for the same block with the same hash, it just needs to update the pages and return back, right? So it's global deduplication, so you have space savings over the entire cluster, and it's inline, so those savings can translate into write performance.
What are you caching there? The hash values?
The fact that this block ID has been written to the cluster, the hash to the, the fact that it's been written. So if another block with the same hash comes in, you can just say, oh, this is already there, and just update pages to map the new block and just return. So there's no replication on each block because it's already written.
So for instance, if you write a block with hash H, right? The first time you see a new hash, you go through the existing pipeline, right? And then the fact that you've seen this hash is already recorded in the metadata service, right? And cached locally in your dedupe cache. A subsequent write for some other random block, if it so happens that the hash matches, there are two ways to check if a hash has already been encountered, right? Either you consult the metadata servers, that's the authoritative state, right? You can avoid that if you find that hash in your local cache. and that we keep state in there as to where the actual data was written on the H block side, so that pointer alone is recorded for the new block on the metadata side.
There's a challenge in my mind because the authoritative knowledge of what the hashes are and what hashes aren't are at the pages level, right?
Yes.
And you're keeping a cache of this information at each of the proxies.
Yes.
If I come in and update a block that happens to be duplicated,
Nothing changes.
well, something has to change. The pointer to that block has to change because it's no longer the same as it once was, right?
Yes,
So it's got a new hash, right? So it comes in, it's got a new hash. The old block still exists until it gets updated. And I guess you're dependent on the updates to those blocks coming through the same proxy, which is a single writer thing.
No,
right?
not really, because you
Yes,
could
really.
no, you could have two virtual disks which are dedupe enabled, and you could have two writes that are coming from two different places with the same hash content, and ultimately the fact whether that hash has already been seen or not is determined by the pages process. So you're either going to find it in your cache. That's where you're going to look up first locally. If you don't find it, you're going to go to the pages processes and figure out if that hash was encountered or not. The fact that that hash value that we record is never going to change.
Right.
Yeah, no, I understand. Maybe we should take this offline. There seems to be a flaw in this logic somehow.
I think, Ray, you'd hit the penalty once every time a proxy hadn't seen a dedupe.
Yeah, no, I understand the
Yes.
penalty. I understand the issue there, but I'm concerned about the fact that you're caching a hash ID which may or may not be pertinent anymore.
Oh, yeah, you
But
might- it
we
might not
ensure
be,
that the
don't know,
cache
do you?
will be invalidated if it's not pertinent anymore.
I think what you're
So
saying
if
is
it gets written from another proxy, the hash is
It's
going to
not
be
invalidated
invalidated?
then. So, for example, right?
It's invalidated at the page, but is it invalidated in all the proxies that happen to
So
maintain it?
I think the way to kind of actually address this is to walk through how a dedupe write actually works on the H block side,
Yeah.
right?
Yeah.
So I
I
will,
guess we don't have to do it here. We can do this off.
Yeah.
but I'll throw you a small bone because you piqued my interest. I have to kind of throw this at you. The way the writes work for dedupe is there is a internal disk that is used which is not exposed to the external client. So there's an external virtual disk, that's what the application is writing to, that gets mapped to an internal system dedupe disk that is shared across all the disks that are deduped. And all these blocks that you write to get mapped to a deduped block on that underlying disk. And that's always going to be
Append.
different, and it's append only. So you will never rewrite anything and step over each other's toes.
That's different.
Can I ask you
Yeah.
a question about?
I mean, the only reason we gave you that answer is because you used the word flaw. And I had to give you that answer.
About write latency or consistency of writes, because with the mechanism that you showed before, you get the proxy and then you get the first write to the first host, and then you propagate the writes.
Right.
Okay, so potentially you have many. First of all, you have many hopes, no? At least 2 or 3, because you have to write to the proxy and then you do
Not write to the proxy. The write is redirected to the H block. H block.
yes,
application.
the redirector. So, but
Yes.
it takes time at the end.
Keep in mind the proxy is local.
No, the proxy is local, but then from the proxy you have to go to the
H block
the
Yes.
H block, and then the H block
Replicates
a
it.
second write, and then you get the hack in some way, no?
Yes.
And so from the latency perspective, so it's all done via Ethernet first of all, and it's many hops. I don't know how can you have a very specific latency measurement in all this process. So I'm not sure that the latency is stable like 1 millisecond,
It is dependent.
2 milliseconds or whatever.
Right. So it is dependent on the policies you selected for the VDIS. So we are giving you a choice because, I mean, if you choose RF6, for example, right, you need to write to 4 nodes. Right? Now, if you want that redundancy, you will have to take the hit in latency.
But to
Right,
answer,
you don't have an hack. So other mechanisms work with a local cache, no?
Yes.
So like if the proxy cache was also right, you get the hack immediately, and you solve
Well,
the
that has
problem.
its own.
So
Yeah.
I'm comparing this with primary storage, okay? So if you get an FC connection and you write to the storage, you know that in that time you get an answer from the system, and it always the same answer if the backend
Couple of things. We don't claim we are sub-millisecond latency. We don't claim that anywhere. Second,
No, I'm not saying that, but just consistency of the latency.
Yes, and we don't, and I think comparison with traditional fiber channel may not be an apples to apples comparison either, right? But we get dedicated consistent performance if there is no real problems with your network, because it's an extremely network solution anyways, right? So if your network's stable, enterprise networks, we don't see variability in performance at all.
Okay.
But are we sub-millisecond? I will say no.
No. I'm not saying about that. I'm saying just to be sure that consistency, because the fact that you are doing at least 2 ops after the first write instead of other system that needs only 1, for example.
Yeah, but then all the other stuff you don't get. You have to, other stuff become an operational burden. Like how do you set up replication? The pipelines are unidirectional and things like that, right?
Can you change the replication factor at a VDIS granularity? Stuff like that, So the consistency will not be there in terms of across VDIS with different policies, because you need to adhere to certain things. But yeah, I mean, fair point that we don't write it to the local cache and act back.
Well, a lot of vendors do kind of absorb things into like a flash tier and then act back, and it's fraught with a lot of problems. I mean, your initial numbers may look extremely great, but what we have learned over the last 3 years in real-world deployments, what will go wrong will absolutely go wrong. And we have been bitten multiple times because we felt like we have seen some problems. We were like, we'll fix it in the next release. You deploy it tomorrow, and day after tomorrow, there's a support ticket saying that exact same thing went wrong. So we have balanced everything, and what we have kept in mind that did not want to break at any cost is correctness of the system. At any point, we will never sacrifice fault tolerance. Right? Never.
We'll show, entire data center is going down, and we'll actually demo that, and it has no impact on correctness.